Okay, so my talk, I think, has a different title in the program, but very similar. It's OpenBSD versus SMP and concurrency. And I kind of decided on the versus just to kind of emphasize that there's kind of like a challenge, and it's like almost adversarial, trying to take the traditional like 20 years of programming like in development that's been centered around like a very one core processor for many years, and then trying to adapt our systems to a new SMP system. So in the SMP universe, 4 times 4 is not 16. This comes from, I used to work at a company that made analysis software, and one of our customers asked if you could run it on a quad-core processor. I think it was like a quad Xeon, 4 gigahertz or something, and he asked, would that make it any faster? And I had to explain, no, because it's single-threaded. I was like, what you want is a 16 gigahertz processor. But Intel has not come out with them yet. So, so this is a challenge where a lot of software has to adapt to being parallel, because you can't just rely on sequential performance improvements. And it's also fraught with peril. I think unlike a lot of other programming bugs and issues that you might encounter, concurrency is kind of like rolling the dice. It seems to work, and then all of a sudden one day you get a race condition or some deadlock due to a timing issue, and it seems very random and chaotic. And so I think developers are still kind of adapting to this, which is a challenging problem. So in the beginning, there was nothing. So what I'm going to cover here for this talk is a couple issues. In the beginning, the first part, I'm going to cover the various concurrency primitives and locking mechanisms, and it's kind of a history lesson in how the BSD kernel has evolved over time. And so the very beginning, we had interrupts, which are kind of like a limited form of preemption, where your kernel is running, or possibly a user-line program is running, and a device wakes up and says, hey, here's a network packet. And so then the kernel jumps to that. So for many years, the only form of like concurrent or reentrant programming in the kernel was interrupt handlers, where you might be running your program, but the kernel could be running a function, and at any instant an interrupt arrives, and then it suddenly jumps off and starts running other code, and you can't really stop this unless you use SPL. So basically what this did was it split the kernel in two, where most of the running code was traditionally called like the top half, and this is like your memory management code and a lot of the file system code and TCP and like the network stack and all that stuff is, I think, would generally be the top half. And then you have a very limited amount of code, which is the bottom half, which is the actual interrupt handlers. Now, I say that I had to qualify most code is top half, and qualify that as being running code, because actually if you look at lines of code in the kernel, just because there's so many device drivers, there are a vast number of interrupt handlers, which would constitute a bottom half. But on any given system, you're not running 90% of the drivers in the source tree. And then there are also sleep and wake up, which is then became T-sleep. But basically, you want to wait for something to happen. So you're a process in the kernel, and what you might want to wait for is an interrupt. So like your file system code writes out a block to disk, but then you have to wait for the disk to be written out and confirmed to be on the disk before you return to the user and say, hey, that fsync is done. And then also, this is used generally for inter-process communication. Like whenever you want to wait for a process to exit, you don't know how long it's going to take, so you sleep, and then whenever a process exits, it says, hey, anybody that's waiting for this, wake up. But the important thing here to note is that things can change while you're waiting. So if you are, for instance, if you grab like a V node or something, or some kernel data structure, and you want to modify it, and then you go to sleep, you have to make sure that you hold a reference or have locked this structure in some manner, because when you wake up, somebody might have deleted the file, or the network socket might have been shut down or something, and so these things can disappear while you're sleeping. And important blinky text here is interrupts must not sleep. So the problem with an interrupt handler is if you go to sleep, basically while the interrupt is running, you're like stealing a process. If you were able to sleep, you would just like grab a random process that you happen to have interrupted and make that process sleep when it didn't want to. And also, you probably won't ever wake up because the interrupts are disabled while interrupt handlers are running. So now, once this happens, your system's going to start running very, very slowly. So then there's also lots of forms of locking, which you can use to protect yourself against others. By protect against others, the other thing can be a CPU or a process. So when I say you want to protect against another CPU on a multi-core system, you have another CPU, you have another core that's modifying stuff at the same time. It has access to all the same memory as you do. So it can be writing to the same memory locations as you are. And you want to prevent that from happening. Or it could be a process in the case of like sleeping. Like you want to grab something, you want to sleep and wait for some event, but you don't want a second process to come in and modify and interfere with your work. So due to the history and length of time that the BSD projects have been in existence, there are a lot of variants of these locks. I know the OpenBSD project has had some issues where developers are using the wrong locks to protect data structures because they don't understand, or perhaps because the man page doesn't make it clear, or perhaps because there is no man page, or for various reasons. There are different locks to protect you from a CPU and from another process. And if you use the wrong lock, you get no protection whatsoever, and so bad things will happen. And so I'm going to try to go through all of the lock variants in the OpenBSD kernel. And I think there's a similar lineup for FreeBSD, NetBSD, and so on. So first, going back, I mentioned SPL. It's the system priority level. And it's actually not a lock. But what this does is it says, don't allow interrupts. And it's generally level-based, although on some architectures it could be mask-based. So what you say is, there's a function or macro SPLNet. And that says disable network interrupts. And so the TCP code would need to use this when it's queuing or dequeuing packets, because you don't want an interrupt to occur and try to enqueue a packet while you're trying to dequeue a packet, because that's a good way to screw up your list structure. Right? But one of the interesting characteristics about these is that they're trivially recursive, which means you can call SPLNet like 28 times in a row, and it doesn't really have any effect. In fact, due to the fact that they're level-based, you can actually do something like SPLNet, then call SPLSoftNet, then call SPLNet again, and that's all okay. As long as you unwind by calling the SPLX function properly in the correct order, you can mix and match various levels of these. So this is actually rather unlike a traditional lock or mutex, where there's no ordering issues with SPL. Generally, and one fact that's not on here is that SPL is on a per processor basis. Next thing is simple locks. These are spin locks that were inherited from Berkeley. They're scattered throughout the kernel. In OpenBSD, they've never been used, they are not used, and they won't be used. And partially this is because they are likely wrong. There are a number of cases where I was reviewing code and noticed that there's a lot of code paths which acquire a lock and then fail to release it on an error path. And this is okay because in OpenBSD, all the simple lock function calls are macros which expand to nothing. But if you ever turn them into actual locks, your kernel will stop functioning in about, well, before you hit init. So, I mean, these are in the kernel, and I think they cause. Sometimes we get patches from people who are trying to fix the spin locks or simple locks, or add them or correct them in various places, and I'm tempted to say that we should just remove them entirely from the kernel so it's not confusing to people. Although, you know, in the one sense, that's just kind of like a lot of churn, and
you're just being lazy.
Oh, yeah, and I mean,
so there are hints, right?
Well, and that's the other point, is that they are hints as to where somebody at one point, without actually running an MP kernel, thought that they might want to lock if they were going to run an MP kernel. And so in some systems we have removed them. I think they're totally gone now from the VFS layer. And so the other part that makes it somewhat difficult to remove these is they're defined as part of the API for some of the kernel interfaces where you pass a simple lock, and if you delete simple locks entirely, then you have nothing to pass there, and whatever. So the other one is Lock Manager, and this is a sleeping lock. So this code does work, although the retirement is fairly imminent in OpenBSD. It's very flexible, but in fact it's almost too flexible. And one of the problems with it is, like, you can have recursive locks, or where if you already hold a lock, you're allowed to acquire it again and again. And as long as you release it the same number of times as you acquire it, everything's okay. Or you can have non-recursive locks, where an attempt to acquire it a second time results in either an error or a panic, depending on how the lock's configured. But you can also pass in flags when you acquire it saying, this lock is generally recursive, or it's recursive, this one function call only, and so it's very hard to tell. And also, so it's somewhat difficult to tell what's actually going on when you see a lock manager call, because you can't really tell what the locking discipline is, like whether you're supposed to be exclusively holding it, or whether it's a shared lock, or whether it's recursive or not. And so we're trying to move away from that. So the replacement for Lock Manager are RW locks, which are reader-writer locks. And they are sleeping, and these are used to block other processes. But they are not, and I repeat this, not for SMP. A RW lock will do nothing to prevent a second CPU from executing in the same set of code. And so this is a replacement for Lock Manager. And so this is the kind of thing that you want to use where you have, where do we use them? We use them all over. But where you have like multiple processes that need to coordinate. And there are also mutexes. And these are spinning locks, which are used to protect against other CPUs. And they have SPL built in. And so what that means is mutexes also are useful on a single processor kernel, because they have the effect of essentially calling SPL like net for you. And this is important because when you are using spin locks, you need to disable any interrupts that might also use the spin lock, because what would happen if you don't, if you acquire a spin lock and then you take an interrupt, and then the interrupt also tries to acquire the spin lock, because it's already acquired, you can't get it again, and then depending on if you're running diagnostic, you get a panic. If you don't, then your CPU spins forever. So it's important to block out interrupts also at the same time that you're acquiring a spin lock. However, you can't sleep holding a mutex. And this is rather different from SPL levels, where you could say SPL net or even like SPL high and then call T-sleep and everything was okay. You would, what T-sleep had magic in it that would set the SPL level back to none. And then when you woke up, you automatically resume at SPL high. However, if you're holding multiple mutexes, msleep doesn't know about all of them. So you're allowed to pass in a single mutex to msleep, and it will be released and then reacquired when you wake up. And so mutexes are not a direct SPL replacement for the sense that they're not recursive, and you have to be careful about the order that you acquire mutexes in. And in fact, it's probably a bad idea to start acquiring more than about 2 anyway, because at some point you're probably going to want to sleep holding exactly 1 mutex and use msleep. But if you're holding several, then you're in trouble. So, I think let me explain a little bit more about why you need to hold 1 mutex and exactly 1 when you call msleep. Usually when you sleep, you are waiting for some condition to occur. And so some other piece of code, like an interrupt, is going to check that the condition, and when the condition is satisfied, it's going to call wake up. However, there is a period of time between when you check that the condition you want to sleep on is true and you call sleep, and then during that time you can be interrupted and by an interrupt which we'll call wake up before you call sleep. And then the wake ups are not stored in any way. So when you sleep, then you have to wait for the next wake up to occur, which might never come. So by using the mutex, you hold a mutex when you check the condition, and then when you know that you need to sleep, you hold the mutex long enough that it's impossible for somebody else to wake you up before you are committed to sleeping, and that way you'll always get the wake up. And of course there are magic locks. The giant lock in the kernel, which protects just about everything, and the scheduler lock have special properties, which I don't really want to get into too much, but they are a little different than other mutexes just because things are a lot more complicated when you are running like the scheduler. It needs to be reentrant for some things, which mutexes generally aren't. So the giant lock is the initial approach, which I think every BSD at least started with. And the general idea here is that we keep all the existing code valid. And so all the code that was written over 20 years that assumed a basically single-threaded kernel still works, because the giant lock keeps this illusion that there's actually only ever 1 CPU running at a time. But lock ordering is important here in that if you, since most entry points acquire the giant lock first, and then you're going to acquire a series of mutexes, any code that doesn't run with the giant lock has to be careful that if you acquire a mutex, you can't then acquire giant after a mutex, or you will create a deadlock. And so in order to run any code without giant, basically you need to ensure that every function that you will ever call can also run without the big lock. And so this makes it a little difficult to test, because at the current time the big lock protects basically everything. And so the important kind of danger point here is that it's basically subsuming all the other mutexes. So if you are going through the kernel and adding mutexes, and you say, oh look, I think the TCP stack has 78 new locks in it, and look, I can run it and everything seems fine, because it's actually still all protected by giant. You won't know if there are any holes in your locking discipline. You won't be aware of any race conditions, because giant is basically not allowing any race conditions to occur. So there's interrupts, locks. What else? Timeouts, I want to mention here, are a way of saying run this function in X ticks from now, or you can say in 100 milliseconds or 6 minutes or something. So this is used in many places. Like whenever you do a select with a timeout in user land, it's run with a timeout. Or, for instance, in like the TCP code, like you send a packet and then you wait 120 seconds before you have to retransmit. And so the timeouts are run from a clock interrupt. So every clock interrupt, the clock interrupt checks to see what timeouts have been scheduled to run for and have basically expired, and then it runs the function. But the code that you provide and say run this function, that function is basically an interrupt, and I think a number of people are not aware of this. And so it's better to just trigger work and to not actually try to do it in a timeout. And so there have been a lot of bugs in OpenBSD where there were some rather overambitious timeouts that tried to do a lot of work. And for instance, so one of the things I should have mentioned it for sleeping, whenever you call malloc, you can pass one of two flags to it. One says sleep for memory, and the other says don't sleep for memory. And in general, you want to pass the sleep for memory flag because it allows you to use a more efficient allocator, and it will never return null. However, in an interrupt handler, like I said, you can't sleep, so you have to pass the don't wait for memory flag. And the overambitious timeouts were calling code that assumed that it was in a non-interrupt context and was calling malloc with the wrong flag. And this works as long as you don't get too far down into the VM code, at which point there's a assertion that you are not in an interrupt handler, and then your system panics. And a recent addition is also work queue, which are kind of complementary to timeouts, and it's basically do this when convenient. There's no hard deadline when it's done. It's just done as soon as the CPU has free cycles. And it unifies a lot of similar code in the kernel where the work queue actually runs from a process context. And so it is allowed to sleep, and you're allowed to do all sorts of interesting things like disk I/O and slow memory allocation and so on from a work queue. And so this replaces a number of tiny kernel threads that we have that were running around in OpenBSD, where there were a lot of these pairings where there's an interrupt occurs and wants to do something, but it can't do it in an interrupt context. So it would have a special thread that would basically loop over sleep, call a function, sleep, call a function, and then the interrupt would just wake it up every time it occurred. And work queue is a way to unify all of this code into a single kernel thread, which makes it, and it has a very easy API to use. So far the uptake has been a little limited. I think just a matter of the existing code works, but a number of developers have used this for some new projects. So I'm going to take a brief side trip here to discuss live lock fix while I was talking about interrupts. So if you get too many interrupts too fast, you get too much work, and then your system actually starts slowing down because you're kind of like under a storm of packets. And so there's various solutions to this, like switching to polling or buying a faster CPU. And the OpenBSD solution, which is new and current, is to kind of shut down the producer. And the way this works is for some network cards that have been converted to this API, you can starve the network card from buffers. And therefore, by not being able to inject new packets into the kernel, it can't create new work, and therefore the kernel has a chance to catch up. This also saves a lot of memory. For instance, I have a gigabit M chip in this laptop, which used to allocate, I don't know, like 4 megabytes of memory or something per interface, because it has normal buffers and jumbo buffers and all sorts of stuff. However, I mean, I'm not even plugged into the network here, so it's a massive waste of memory because there are not any jumbo frames arriving at my laptop right now. Yeah.
So, how do I ask this question? That solution, isn't that solution going to cause you to get large numbers of false errors on many modern interfaces?
So that's one of the things. So
basically, RX overflow.
Yeah. So what? There were a couple drivers that kind of had bugs in them that always assumed they had a full ring, and so basically this cuts the ring size down to, I think the default ring size now is about 4.
Well, it grows on demand.
But it grows on demand.
Oh, okay.
So if you can fill the ring, then you get granted a new packet or a new buffer.
Right.
But the default on, I think like BGE I think didn't work with a ring smaller than 7 or something. But for M and I think some of the other ones they start off with 4, and that's actually enough for almost for the majority of like normal traffic, unless you're like routing a gigabit. But
The other question is, are these on devices that don't support interrupt coalescing?
It is. It's complementary to that, because I think one of the problems, like even with the interrupt coalescing, the problem then is you just get like dumped like 64 packets on you at a time, and then you process 2 of them, and then you get another 64 dumped on you, and then you overflow the IP queue, and they get dropped anyway. So it was easier to just spend less time in the interrupt handler by telling the card, hey, you're done. Like you get 4, you give us 4 packets, then go away.
And is this common across a large number of NICs in OpenBSD, or just a few misbehaving NICs?
Not yet. I
mean, is the problem, not this solution, common across a large number of NICs? Do you see this often?
I don't know how many. It's only on a couple. I'm not sure what you mean by the problem.
It's not a hardware-specific problem. The problem is that your machine has more to do than it can handle.
Yes.
So in the end, you end up your interrupt handler running all the time, showing you new packets into the IP interrupt queue, but you never get around and never get CPU cycles to actually group them off. So you drop them anyway.
I understand LiveLock.
Yeah, Now we forced the NIC to give us less, like we adapted to the level we can handle, so in the end we get more work done.
So the thing I'm a little confused about, and I'll just ask it straight out, is why can't you handle that many? Because, at least on FreeBSD, we don't have this problem on even the most powerful modern NICs.
That just depends on the.
So is it just because you're using? It's like someone's using a slow processor kind of thing.
Well, I mean, you can get every
or whatever. I mean, if you're getting like a 10 gig stream of ACK packets or something, I don't think we can.
A 10 gig stream at the moment. That's why I'm confused by this.
What do you mean?
Like on one of these dual processor quad core boxes with a Chelsea card, I have no problem sucking up all the data. The machine never gets into LiveLock, and it's not the network stack that's under a huge amount of pressure, or the device drive. So that's why I'm asking if it's across a certain number of NICs.
No, I think it's just generally that.
I'm pretty sure you can't handle that at 64 byte packets.
Well, no, I can show you that later.
So
anyway,
it's not a huge problem in practice, but the people that are running into that run like high bandwidth routers are annoyed enough by it that they want a solution. It basically gives you the headroom for DDoS.
Okay.
Yeah, that's what it is.
So as for why we can't keep up, I don't actually know.
Yeah,
I'm not really like a big network guy. I threw this in here just because I was discussing interrupts, and it was new and no one else is going to talk about it, I guess. Maybe well, but so I think this is just kind of like a new cool thing that we have, and I think like we had discussed like polling, for instance, as an alternative to this, and I think this is a kind of a cooler thing because it gives you still keeps the low latency. It just gives you a more refined stream of packets as opposed to giant dumps of packets every once in a while.
So big things is KVA, right? That's a huge deal.
So path forward for SMP, sidetrack, is maybe more Mutexes, less giant. I think so far there's been a little bit of progress, locking down some of the subsystems. Some of them are not, and it's kind of herding cats if trying to get developers to work on this. And so different developers have different pieces working, but it's a little hard to test. And I think talking to some of the other developers, it's not clear necessarily that we want to follow the traditional model of you have a struct foobar, therefore you put a struct foobar lock inside the struct foobar. We're taking our time. Let me throw in a note here about preemption. So this is not likely to appear in OpenBSD soon. So OpenBSD does not use interrupt threads. I know FreeBSD went to interrupt threads fairly early, I think. So we are still running all of the interrupt code from the interrupt handler. Like, we don't queue an interrupt thread to run. And so I think this avoids some of the problems that you need. You introduce preemption to solve the problems where you have interrupt threads with the wrong priority or that aren't running correctly. So we're, for the moment, avoiding doing that work. So little SMP recap. You can get SMP support via the giant lock, and there are mutexes available to lock subsystems, but at this point they don't matter a whole lot. So I'm going to switch gears now to talk about rthreads, which was sadly introduced 4 years ago at EuroBSDCon Basel.
May I cite you?
What?
Now that I talked about it, I have to finish it.
It's usually how that works.
Yes, so I should have introduced myself as saying I'm an OpenBSD developer who starts things and then gives a talk and then that is the last piece of work I've ever seen. So the basic idea here was that the libp thread implementation we have, which is entirely user-land, complements of FreeBSD, was working great, but has a number of issues. One, it completely cannot scale to SMP. You only have a single process, so you only have a single running context in the kernel, and it plays nasty games with setting file descriptors to non-blocking in order to fake out thread switches. Whenever you read or write to a file, it checks to see if it's non-blocking or not, and then tries to do some select magic, and it's kind of cooperative multi-threading. And the problem there is when you write to disk, select always returns true for files descriptors that go to disk, and so this means that anytime you do disk IO in a thread, the entire process blocks until it gets done, which kind of defeats the purpose of using threading, which is that you wanted to keep working while the disk IO is in progress. And it relies entirely on the kernel for thread switching and for a lot of the work of doing work. So it's a one-to-one threading implementation. And when I said this 4 years ago, I think FreeBSD and NetBSD both had M-to-N threading models, and I had a slide that said, "Oh, that's too complex. I want to get this done, so I'm going to do the easy way." The somewhat ironic part is now NetBSD and FreeBSD are both kind of moving more to one-to-one threading libraries. So I was right, but I didn't get done, so I can't. I can't really laugh at you guys too much. But on the upside, why this is better than the existing pthread stuff. It provides a sleeping context per thread. So now you can have 7 threads blocked on disk I/O and 2 waiting for network I/O and 1 drawing a pretty spinning ball on your screen all at the same time. And so there's a lot. There aren't any bugs caused by working around the previous issue, which is that you don't have a sleeping context. And so libpthread is just a mountain of code that does all these little tricks, and you can take advantage of SMP. On the downside, it's a little harder to test development because everything is now basically the library is really just kind of like almost stubs for kernel functions. And so in order to test this, you have to reboot your kernel, which makes it a little harder to develop. And you want to be more careful here because I think, for instance, there's still a problem where if you rthreads is not enabled by default. One of the reasons for that is if you create you can create locks, and the locks basically kind of live in the kernel. And if you create too many locks, you can run the kernel out of memory. And so we have to be careful that now that all this we're exposing more of the kernel scheduler mechanism to user land, we have to be careful that we don't introduce security bugs or other problems in the process. So rthread status is still coming along. And actually, I think one of the reasons that progress has been slow is I personally have kind of lost motivation in this. At one point, I started the project because I wanted XMMS to work. And I wanted to be able to scroll my playlist without it jamming up the music. And this is a very pressing issue for me. But as I'll show you in the next slide, I think I got that working very quickly because it was a very simple consumer of threads, and then kind of lost interest. And then I bought an iPod, and so I don't even use XMS anymore. And also, the only other threaded app that I actually use now is Firefox, and Firefox's threading is pretty abysmal. And I think the main problem there is they still single thread the resolver, and so the reason that Firefox is like balls slow is because it single threads all the DNS lookups, and so if you look up a non-existent domain or you hit some ads.double click or whatever, that their DNS servers suck, so it takes forever, and then basically it kind of locks up all the other DNS requests. And rthreads can't help with that because it's a Firefox problem, and so I can't fix it, so I'm not going into that code. But rthreads has pretty much been the ultimate 80-20 rule. I would say that the progress made in the first week, and then the 2 months after that, and the 4 years after that has been about equal. Basically, I had a short prototype working in a week, which then kind of maybe gave me the idea I could give a talk about it. And then I spent about 2 months polishing it off and making it almost real, so that I could demo it at the talk, and it went pretty well. And then it's been about 4 years now, and it's gotten a little better. So initially, the way it worked was there weren't really threads. Basically, you just had a whole conglomerate of processes that just happen to share an address space created by the rfork system call. And then this led to some interesting side effects because the kernel wasn't actually thread aware. But so now the process thread separation is mostly done in the kernel, where the kernel knows that if one thread, for instance, segfaults, that you have to tear down the whole process, and you can't let the other threads keep running. And the hard part that's left, and I've been saying this for a long time, is signals. And I think I'm now at the point where I've said it enough. I actually believe that if we fix signals, it'll be done. But the performance is still mostly untested. I did, just for fun, a brief benchmark using the Intel thread building blocks library, which is a pretty cool library if you are into C++. And it gives you a bunch of parallel sorting algorithms and stuff. And so just on sample data sets, I was able to demonstrate that using rthreads, you can sort an array of 1 million integers in half the time on a dual processor machine. So okay, so this is back kind of to the way forward on SMP. So the easy challenges, which I think we were looking for a volunteer to pick up, would be generic IPIs. So IPI is a way of one processor telling another processor to run some code. And so we have a bunch of these. Like for instance, when you change the when you mmap some new data, or generally you have to invalidate like a TLB. You have to send TLB shoot down IPIs to other processors. And so there's a number of these in the kernel already, but they're kind of hardwired. Like you can't generically tell a processor to run some other code. And you can see this if you have any a modern laptop that has a Core 2 processor. You get CPU temperatures, which are built in on die. But you will always get the same temperature for both CPUs. And that's because it's actually one CPU out of the two. One of the two cores is actually reading the value for both processors, and so of course it reads the same temperature. And there's ways to work around this, but I haven't fixed it yet because we're waiting for generic IPIs, and that was more than 10 lines of code. So. And then there's also some issues in userland. One of these is top. I think, which we're going to have a problem pretty soon with these SPARC 64 machines that have 128 thread processors on them, because you're going to need a X-term that's at least 128 rows high in order to even see the first process that's actually on CPU. And another one was APM, and actually a guy sent me... What?
They got fixed yesterday.
Yeah, so I was going to say I just checked in a patch that somebody sent in where APMD on OpenBSD can automatically scale your CPU frequency based on CPU utilization. But the problem is, basically it has a threshold where if you're using more than half your CPU, it'll start increasing the frequency in order to keep up with the work. But on pretty much every laptop now that has a dual-core processor, you can be totally pegging one CPU, but your total utilization will never get above 50%. And so the old APM algorithm would not increase your frequency, because it's like, oh, look, you're only using 50% of the CPU. You're half idle. And meanwhile, Firefox is scrolling at 2 seconds per frame, the kind of stuff. So there's a patch that someone sent in that changed this to basically take the min value of any CPU, which is much more efficient. And one of the other things that we could use is something like FreeBSD's Witness, which I talked to a couple of their developers, said has fixed helped them a lot with locking problems in the kernel. So right now, our locks are rather unforgiving in that if you attempt to acquire them incorrectly, one of two things will happen. You will panic or you will lock up. But you will not get any kind of informational message other than, well, if you get a panic, you'll get a message that says don't do that, and if you lock up, you get nothing. So this makes debugging some of these issues a little harder, and it also means that you have to rely in some cases on bad luck to uncover these timing issues where a better debug locks would do a much better job here.
So I think we can find bad luck as your problem.
Yeah, there's one machine that has worse luck than any other.
Is there a reason? I mean, is the locking system just too different not to just take Witness? I mean, it's BSD licensed.
Yeah, I haven't actually looked at it. For whatever reason, I think this is a case of
it has to be done.
So it just isn't done. It's not that.
That has to be done, and also I think for whatever reason, we decided to grow our own locks, so we have slightly different mutexes and yeah. I mean, I think they have almost the exact same name, but it probably has the flags and the pointer in a different spot.
Yeah, because trust me, you don't want to reproduce it again. Steal as much as you can from us because you really don't have to do it twice.
Yeah, I definitely think I would not attempt writing this. I would definitely port it before I was going to write it, but it's just a matter of not having it. So some things that are left to appear. Sadly, the scheduler is still the original BSD one, which is not processor aware, so there's no scheduler or processor affinity, although it's work in progress, and also NUMA. So some of these larger CPUs, there's memory here and memory there, and it's not all the same. And there's a diff out that's slowly being integrated to address some of this stuff. So you want to run SMP. Which one do you want to run it on? i386, AMD64. I think it's, unless you buy like one of these 4-inch netbook things, you're getting a dual-core processor at the minimum, and it's pretty stable. I think almost every developer runs it on a daily basis, and SMP there is pretty solid. Spark 64 blinks yellow sometimes. So the Spark 64, the traditional Ultra Spark machines that are dual processor, I think work pretty well, but you're limited to 700 megahertz or something on this rather ancient thing that...
No, it's a bit over gigahertz.
Okay. But I think, in general, the modern ones are all like the T1, the T2, where the support here is fairly new, so you're going to want to run current if you're running on...
Actually, the Fujitsu Spark 64 are pretty fast. I forgot the clock rates.
Okay.
But they're still the traditional, low number of CPUs.
Okay. But they're loud, so I don't have one.
It's hard to get.
Yeah, they don't carry around well. Then we get down into Mac PPC and M88K, where I think Mac, I don't think actually really works yet. You might be able to get to init, but probably not much beyond. And I don't have one. And M88K actually does work, but you don't have one, trust me. So, those if you can find them on eBay and then get all the processor boards for them, actually do work. So, in terms of CPU support, the good ones are like the Core 2, where you have 2 full cores on the chip. The cache is unified between the cores, and all the memory is local. So this, somewhat helps us in the fact that we don't have processor affinity yet. The bouncing still hurts, but it's not as bad because at least you can share the cache. The hyper-threading CPUs are not a particularly good fit at this time because what will tend to happen is OpenBSD, the scheduler, will put 2 processes on both threads of one core and it will leave the other core unused. It's not thread versus core aware. And this also applies to, I think, the Spark machines as well, the new Spark T2s. And then it gets kind of ugly with the NUMA, where you have memory and other things. And Mito was talking about some SGI thing that he's actually has one or something where it's like the memory is in this room and the processor's in that room, and you have some long cable to connect them. Those I think the performance there is kind of degrading as we go. And despite I think the first multiprocessor system came out 50 years ago, probably but it's still a continuous research area. And I think one of the things here is there's other forms of synchronization than just the locks that I've talked about, and there's more complex variants of those, and there's also lock-free data structures which people like to ask about on mailing lists, but I haven't seen code for any of them for OpenBSD. So and also I think I mentioned the thread building blocks that Intel has, which I think is a great way if you're developing userland threaded code, is to move away from just having threads running around because there's no end to problems with that, and move more kind of like a task-oriented design where the threading is implicit, but you don't have to explicitly manage the threads. So if wishes were fishes, we'd have fine-grained locking. I think pool and some of the memory management stuff is actually there. So you can allocate memory but there's not a whole lot else you can do. And other subsystems are farther off. And of course, user requests, always welcome, but not really. Just kidding. So that's the end of my talk. I unfortunately I didn't actually clear this with any other OpenBSD developers, so I don't know. I think I've described the current state of the system, but Henning nods. But feel free to ask questions, and I'll try to come up with an answer.
But now you're writing all the code you talked about.
Yeah, now I've talked about it, so now I'm going to have to finish it.
Now you're going to disappear for another 4 years?
Well.
Can you talk about threads for a few minutes?
They're...
You have to finish on that.
Yeah. Right.
So how many people do you have actually working on this in this area?
I give talks. We have a new guy, Philip Gunther, who started making some rthreads diffs, and he's actually doing some good work, but he's busy at work now, I think. So he's doing it only part-time. I think, definitely one of the things is there's no one working full-time or professionally on any of this. This is all volunteer work. The other developer that's done a lot of the SMP work is Art, who doesn't get paid to work on it either. He's disappeared. And Mark Hetness, who did the Spark 64 support. He's been working a lot on that, but that's just getting the hardware up and running, and hasn't been so much architectural changes. And then Ariane posted a NUMA diff. So it's a handful of people that have diffs that are in various states of completion, but I would say it's definitely less than one full-time person by far. It's
like 10 different developers in that area, right?
And the DLG as well.
Yeah.
There's a couple of people here and there, but I would say total effort in a week amounts to maybe a half-man week per real week of time. So that is holding up progress a little bit. Are you really done?